Hello, this is Mr. Collier, and today we're going to look at the normal distribution. So here we look at there's some various distributions of different types of data here. Here's the distribution of heights of men and women. Okay, so men are a bit taller than women, but similar distribution, right? So these are frequencies. All these graphs have frequencies. So you can see here the most frequent male height is about 72 inches or so. Okay, so that's right there. So that would be the mode and the mean and the median actually in this case. And you look at some other distributions like this here is sedimentation rate, and this is birth weights of babies. Okay, and those are the frequencies. This is molecular weight over here, and this is length of stay in hospital and such. Okay, so if you notice, there's a similarity between some of these. These three graphs all have a similar shape. It's sometimes called the bell curve because it looks like an upside down bell. It's also called the normal curve, or sometimes also the Gaussian distribution after Carl Friedrich Gauss. So this is a normal distribution. Okay, and the thing about the normal distribution that makes it different than these two is that it's symmetrical. Okay, the maximum part here is the mean, median, and the mode. Okay, so that's going to be the mean, median, and the mode is right in the middle. And it's symmetrical as in you got an equal amount above and below this point, and it's totally symmetrical or close enough to symmetrical. Okay, and that's not the case for these. For example, here we have mean, median, and mode are not the same in this distribution. Okay, so this kind of distribution happens a lot, especially heights of people, heights of trees and weights and stuff like that. Even probability comes up as well. So it comes up a lot, so it's a very special type of distribution called the normal distribution. Okay, and here are the approximate percentages. This is for a perfect normal distribution, but we can use this to approximate other normal distributions. And here, this is the mean, right? Also, this symbol is also sometimes used for the mean. And this is standard deviation, which is also sometimes you see it as omega. Okay, so that's these here are standard deviations. Alright, so what's happening here is we say now that's 34% is above the mean and 34% below the mean here. So we say 68% is within one standard deviation of the mean. Okay, and that's 34% is one standard deviation above the mean, 34% is one standard deviation below the mean. And you can see here, oh yes, and here 95% is within two standard deviations of the mean. Alright, and you can see here that you've got some more percentages in this. We have 99.7 is within 3 standard deviations of the mean. Okay, so 99.7 is within 3 standard deviations. For example, the IQ scores are supposed to be normally distributed, and they define the mean value as 100, an IQ of 100. Okay, so if you're above, I think if you're above 2 standard deviations above the mean, which is 130, I think that's considered genius. And, or maybe it's 145. But as you can see, if you get to 145, you get 145, that's 3 standard deviations above the mean. So if you have an IQ of 145, you're better than 90, actually you're better than, even more than 99.7% because you're also better than this bit as well. So above 145 there's only 0.15% of the population. So if you have an IQ of 145, you're better than 99.85% of the population. Okay, so that's how you kind of interpret things with the normal distribution. We're going to take a look at some examples in a second. Here's some properties of the normal distribution. Bell-shaped curve, symmetrical about the mean. So we're just talking about most of this stuff. Alright. So on to some examples. Suppose scores on an IQ test are normally distributed. The test has a mean of 100, standard deviation, sometimes called S or omega, standard deviation of 10. Okay, so that means, okay, if the standard deviation is 10 and the mean is 100, then 100 is right here in the mean. Here's going to be 110, and there's going to be 90, and there's going to be 120 and 80 and so forth. Okay, so what's the probability that a person takes a score between 90 and 110? Well, here's the region that's between 90 and 110, and if we check our diagram here, we have 68%, so that's 68%, so part A, yeah, 68%, there's 68% probability, or you could say 68% of the people are between 90 and 110. Okay, so part B says what's the probability of an IQ greater than 120? So greater than 120, well, this is 110. This is 120. Okay, if we look at this thing here, okay, so let's do two standard deviations right here. We can add up these two parts. This is about 2.5%, right? Well, we know that, yeah, that's right, 2.5%. We know that 95% is within two standard deviations, okay? So above two standard deviations above the mean above that is half of 5%, which is 2.5%. So for part B, 2.5% probability that the person is above IQ 120. Alright, so if we look at part C, what's the probability between 90 and 120? So 90 is one standard deviation below the mean. Alright, and this is 110, and this is 120. Alright, so we know that 68% is here. Now what was the question again? I've forgotten the question. What's the probability between, okay, between 90 and 120. Right, yeah. So between 90 and 110 is a 68% chance between 90 and 110. And then we'll add on this part, okay? We know within two standard deviations is 95%. So we know that's going to be 95% between there. And so these two bits here, so let's go back and look at this thing here. So this bit here is 13.5%, right? And then here it's the 68%, so we'll just add that 13.5% on. So this is going to be 68% plus 13.5%, which equals 81.5%. So it's an 85.1% chance of the IQ being between 90 and 120. Okay, next we're doing this example. In part A, we have to sketch the normal distribution for this information. So waiting times for an elevator are normally distributed, the mean of 1.5 minutes and a standard deviation of 20 seconds. So the mean is 1.5 minutes. So I'm going to change that to, that's 90 seconds, right? So that might be a bit easier to do that, I think. So let me draw a normal curve here. Try to make it look as symmetrical as possible. Maybe that wasn't the best normal curve ever here. So anyway, here's the mean. Actually, let me draw it a little bit differently. Alright. So here's the mean. The mean's 90 seconds, right? So 90 seconds. And it says indicating clearly the mean and one standard deviation, two standard deviations. Okay. Alright, so maybe I'll keep labeling this, and I'll go down here at 20 seconds above there, 110 seconds. So 1 standard deviation, then we have 120, and then we have 130. Okay, and below that, oops, that's not quite right. That should be, it's going up by 20, so 130, 150. Alright, and then down here, that would be 70, 50, 30. Alright, and maybe I should label the standard deviations as well. This is the mean. Alright, I'm going to call that, the mean, or you could use this symbol for mean. And here is the mean plus 1 standard deviation. This is the mean plus 2 standard deviations. This is the mean plus 3 standard deviations. And over here you can do mean minus 1 standard deviation, mean minus 2 standard deviations, mean minus 3 standard deviations. Alright, so I've got all that in there. Next, part B. Find the probability that a person waits longer than 2 minutes 10 seconds. So I'm going to write that as P for probability. Waiting time is greater than 2 minutes 10 seconds is 130 seconds. Alright, so we'll work that out. And if we look at our graph, longer than 2 minutes 10 seconds, or 130 seconds. So we're looking at this region right here. So what's the probability in that region? Well, we can look at our normal curve and take a look at that again. Well, actually, this is 34%, right? 34%. This is 13.5 here. And if you remember, this one's going to be 2.35%, and that one's 0.1%, or 0.15%. So it's actually 2.5% probability that the person waits 2 minutes 10 seconds. Part C, find the probability that a person waits less than 1 minute 10 seconds. So 1 minute 10 seconds is 70 seconds. So we're looking at this region over here, 70 seconds. So again, this part here is 13.5%. That's 2.35, and that's 0.15. So the probability that the waiting time is less than 70 seconds is going to be 13.5 plus 2.35 plus 0.15%, which is this is 2.5 plus this is going to give me 16%. 16% chance. Okay, part D. Calculate the number of people expected to wait less than 50 seconds for the elevator. Alright, let's look at the probability of less than time is less than 50 seconds. Okay, so less than 50 seconds is over here. The last two bits, which is, we know that that part is 2.5%. So there's a 2.5% chance of waiting less than 50 seconds. If 200 people use the elevator, then we just need to multiply 2.5% times 200. Alright, so let's do it on the calculator. So 2.5%, you want to change that to a decimal, then you got to divide by 100. Okay, so 0.025 and multiply that by 200. You get 5, so 5 people. 5 people will have waited less than 5 seconds. That's less than 50 seconds. So 5 people. Okay, let's take a look at one more example. The heights of 250 20-year-old women are normally distributed with a mean of 1.68 meters, and there's a standard deviation. Sketch the normal curve, clearly indicating the mean and the heights and so forth. Okay, it's like we did before. So here's the curve. Now, in the middle, right here, is the mean, which is 1.68 meters, or 1.68. These are heights. Yeah, heights. Okay, so 1.68. Alright, so this is the mean. You can also use this symbol. And our standard deviation is 0.06. So the next one is going to be 1.74. And then I keep going up 6, right? So the next one's going to be 1.8, and then 1.86. And go backwards by 0.06s, so 1.62, 1.56, and 1.5. Okay? So I've got all of them in there. Let's label that as x, or the mean plus one standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations. Here is the mean minus 1 standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. Alright. Alright, and part B. Find the probability that a woman has a height between 1.56. So probability that the height is between 1.56 and 1.74. Okay, so I'm going to work that out. So 1.56 is over here, and 1.74 is there, so I'm working at this probability. Alright, so in a normal distribution, this is going to be, well, this here is going to be 34%, 34%, and this one's 13.5%. So I'll just add those together, 13.5% plus, well, 64 and 64, the middle part is 68%. So that is 81.5%. Alright, part C. Find the expected number of women with a height greater than 1.8 meters. So that would be this region right here. So the probability that the height is greater than 1.8 meters is going to be equal to 2.35% plus 0.15%. Okay, that's 2.35, and that's 0.15. We'll add that together with 2.50%, or just 2.5%. And if there were 250 people in total, we have to take 250 times 2.5% to get the total number of women expected there. So 2.5% is 0.025, and then I'm going to multiply that by 250, and that gives me 6.25. Now that's 6.25. Perhaps we'll want to say about 6 women. Okay, about 6 women will be greater than 1.8 meters tall.